recording. So let's go ahead and get started. I found that Google or YouTube, the YouTube automated closed captioning, the accuracy has improved quite a bit from like a few years back. I tried it out and it was really, really bad. And I tried to turn it on for some of my own videos, like something that I recorded last week. And I thought the accuracy is actually pretty good. I mean, it actually has improved quite a bit over the past 2 years or so. So for those of you who want to just kind of watch it with the closed captioning, you can give it a try. It's not 100% accurate, but I think it has improved quite a bit. All right, so what we'll do today is we'll continue the discussion of operators, and you might have learned most of the operators useful for arithmetic operations from cisp300 or 301, okay, which are multiplication, division, and stuff like that. In this class, we are going to focus on something that you may not have learned in your previous class. We'll start with logical operators, and then we'll continue on to bitwise operators. Right. So we are still on basic syntax, expressions and operators. And last time I think we were talking about integer types, so we'll go back to this particular slide and start with that one, and then we can move forward with the other stuff. Last time we definitely talked about base conversion. So base conversion is actually pretty easy. What you need to do is to remember you're not doing base conversion. You're only dealing with specifying values using quantities of powers of 2. That's all you're going to do. And to relate that back to what we usually do is in base 10 numbers, we use quantities of powers of 10 instead to specify values. But in base 2, you have to specify the numbers of powers of 2 in order to express a particular value. Are there any questions about the base conversion part? Because your next homework assignment has base conversion stuff in it. So if you have questions, this is a good time to ask. No questions? This is all good? Okay. And then we also talked about base conversion from base 2 to base 10. And the trick is every digit in a base 2 number, a binary number, is essentially telling you how many powers of 2, how many of each power of 2 do we have in the value that we want to represent. So the first one, the rightmost one is the least significant bit. It's always going to tell you how many 1s we have. The next one tells you how many 2s, how many 4s is the next one, how many 8s, how many 16s, 32s, 64s, and so on. If this is a quote-unquote decimal number, I really cannot use decimal number anymore because it's actually binary. But if there's a dot, a period, or a point, then whatever is on the right-hand side of the point tells you how many halves, how many quarters, how many eighths, how many 16ths, and so on. So it's not really that much different from a base 10 number. It is just that we're not dealing with powers of 10. Instead, we're dealing with powers of 2 in a binary number. Yes?
For example, once you get to how many 128s, if there's another 1, that means
how many 256, 512, 1024, and so on.
Okay.
Right. And then we talked about integer width. Okay, in other words, how many bits are we using for a particular integer? And this is a very important issue. Yes, go ahead.
I think last lecture we made it all the way to signed to unsigned.
We made it all the way to signed to unsigned? Okay, so let's go ahead and fast forward.
The whole circle for that one.
Okay, excellent. And that's one thing you can remember too. Instead of a number line, remember in programming it is a number circle. Always keep that in mind, because if you run out of values, it will go all the way to the other side. So instead of the largest integer, you will roll to the smallest or most negative integer. All right, so let's move on to the next one. So we are now ready for logical versus bitwise operators, which is the next module. it is always helpful to read a little bit ahead of me. Okay, if I talk about a particular slide in the previous class, if you just kind of look at the next one, it will help quite a bit because you know what I'm going to talk about. The first part of this is really a repetition. It talks about what a bit or binary digit is. So I'm going to skip this part because we have talked about this part already. So we'll go ahead and skip this part here. And we also talked about integer representation. So that's also done. So we'll skip that part as well. So now we'll go back and talk about what is logical versus bitwise operator. And we'll start with something that you should be familiar with already, except how it is represented, or the syntax of this may look a little bit foreign. But other than that, the concept should not be foreign to you. Logical operators are called logical operators because they are corresponding to what we use in normal conversation as and, that's conjunction, or, which is disjunction, or not, which is negation. So those logical operators we use on a daily basis already. It's just that when in programming we give them like very specific and awkward and longer names like conjunction, disjunction, and negation. So we'll start with a truth table for logical and, otherwise known as conjunction. In your programming class, in the previous programming class, cisp300 or 301, most instructors will simply spell it out as and. Are there any questions about what I'm about to describe? Okay. Now, in your previous class, because they will be dealing with true and false, then you probably learn it as true and true is true, true and false is false, false and true is false, false and false is false. But in this class, because we're specifically dealing with C and C++, things get a little bit different, okay? But not much. Every time you see a value of 0, it is false. Okay, so in C and C++ programming, 0 is basically the same thing as false. Then what is true? Well, anything other than 0 is considered true. So 1 is considered true, 5 is considered true, -5 is considered true, and so on. So anything other than 0 is considered true. So when you look at numbers like that, okay, then we can define this truth table because we have false and false is false because 0 is false. 0 and anything that is non-zero is false. Anything that is non-zero and false is false. Anything that is non-zero and anything that is non-zero is anything that is non-zero. Okay, hold on a second here. What do you mean by non-zero? So in other words, if I have 5 on one side of conjunction and 10 on the other side of conjunction, what is the result of that particular operator? I cannot even tell you. The only thing I can tell you is it is not 0. Okay? So there's no obligation whatsoever from the C compiler to give you a particular non-zero value. It can be any non-zero value. That said, most compilers give you probably a 1 or -1, okay, because of the representation of bits. The next one is OR, okay, which is known as disjunction. If you have taken the class in logic, in philosophy, or math classes, you're probably kind of familiar with these names too. Disjunction is basically just OR. We spell it out as OR, that OR. So this is kind of like the flip side of AND in a way, because false or false is false, but all the other combinations will give you true. And you have to remember, this is not exclusive OR. In other words, we are not talking about either or. This is just a regular OR, where if at least one side of disjunction is true, the whole thing is true. And the last one is logical NOT, which is known as negation. In your previous class, you probably spelled it out as just NOT, N-O-T, but in this class, we use an exclamation point to mean negation, and that is a C, C++ syntax. So you have to use double ampersand, double bar, and a single exclamation point for conjunction, disjunction, and negation, respectively. Do we have any questions at this point? No questions? All right. we talked about assignment operations already. So we can actually test these things just a little bit. So what I'll do during the lab time is I'm going to show you guys how to test the result of an expression using the C compiler and using GDB, which may come in handy when you're doing your homework, which is in the form of a quiz this time. So I will leave that up to the lab time to do it, and then for now I'm going to move on and talk about bitwise operations, unless there are questions about logical operators. Are there any questions about logical operators? No questions? Okay. So for the most part, we just have to get used to the syntax. Okay. Remember to use 2 ampersand, 2 double bar, and the exclamation point. Now, what you really have to be careful about are these guys. Okay. If you just use 1 single ampersand, which looks right in a program, it will do the wrong thing. It is syntactically correct, but it won't do what you think it should be doing. Okay? So we'll talk about that after we talk about bitwise operations. So now we'll move on to bitwise operators. Now bitwise operators is kind of like a low-level thing, because most programming do not involve, okay, we have to look at an integer and break it up into individual bits. But in C, C++ programs, we have to do that quite often, because C and C++, or C in particular, was a low-level programming language designed to write operating systems. Now, when you're writing an operating system, there are many cases where you need to control individual bits inside a 16-bit integer or 8-bit integer or something like that. So that's why bitwise operators are fairly commonly used in C programs. In C++, not as much, but there are still, it's still a very useful feature that you have to understand. All right, so there's a lot of text here. How many people still remember the concept of an array? Okay, so most of you probably should have exposed to the concept of an array. So one thing you can do is to see an integer, okay, like a 16-bit integer, as an array. Okay, so kind of look at an integer as an array of bits. Okay, so instead of looking at a 16-bit integer as a single number that cannot be broken up into smaller parts, look at it as 16 individual binary digits, 16 individual zeros and ones. And what bitwise operators do is they can work on each individual bit separately, independent from what it does to the other bits. So let's take a look at this particular definition here. So you can see that this table for bitwise AND is about the same as the other table for logical AND. There are several differences. Okay, so let me just kind of let's see. I will display this, side by side with another tab. Because I want to show you side by side what they look like. And let's just shrink this one, put this one on the side. And on the first one, on the left-hand side, I'm going to show the bitwise operator. And then on the other side, I will show the logical operator. So this way you can actually get a really good sense of, how close they are, and yet they're slightly different. So look at these two, okay? Let me just kind of point out which one we're talking about here. This is bitwise AND, and this is logical AND. You can see that the column heading is a little bit different, because with bitwise AND, I say it is bit I of X, which means it is an individual bit of an integer. If you're dealing with a 32-bit integer, then you can you have to apply this table to each and every bit of a 32-bit number. If you're dealing with an 8-bit number, then you have to do this, to all 8 bits of a particular number. And that's why in this case, before we say non-zero, but this time there's only 1. Why do you think I can say for sure that non-zero has to be 1 when we're dealing with bitwise operation? Exactly, because in a binary number, we can only have 2 values per digit, which is 0 and 1. If a particular value is not 0, how many choices do I have? We only got 1 choice, which is 1, right? The value of 1. So that's why when you're dealing with bitwise operation, for each individual bit, bit 0 and 0 has to be 0, 0 and 1 has to be 0, and the last one is 1 and 1 has to be a 1. Okay? And if you look at bitwise OR, which is this one here, this is bitwise OR definition, this is logical OR definition, and you can see how similar they look like, and yet they're different. Because with this table, we're dealing with each individual bit. With this table, we are dealing with an entire integer. But the operator itself is also confusingly similar, because the bitwise operation is the single version of the logical operation. And that's where most people make mistakes, is they forget, right? Double ampersand, instead they would type one single ampersand, which is logically, syntactically, it is still correct, but it means something that is different. All right? Okay. Let's work out a few examples, just so that we understand, why confusing a logical operator with a bitwise operator can lead to massive confusion. Okay. All right. So we'll work out a few examples here. I'm just going to use a mouse pad here, kind of the same as Notepad in Windows, and we'll work out a few examples. And what I'll do is I'll start with, I don't know, let's try 9 ampersand 1. Okay. So we want to figure out what is the bitwise AND of 9 and 1. And just to make sure that I don't waste too much time doing, writing zeros and ones, we'll deal with 8-bit integers. Okay, because it's the same approach to 16-bit or 32-bit or 64-bit number. What is the 8-bit representation of 9? 1001 as the least significant bits, everything else being zeros. Okay. So 9 in base 10 is 0000, 1001 in base 2. Because 9 has 1 1 and 1 8. That's how you can determine how to write it. 1 is easy. Okay, that's 1 in base 2. So, in other words, if you want to perform bitwise operation, the first thing you have to do is to look at a value in binary. You cannot do it in base 10. Okay, you can sort of do it in base 16 if you have a really good memory, but I would just convert everything to base 2 first, and then you can perform the bitwise operation. So now we have to perform the bitwise operation. So I'm going to write it almost the same way as you would write, addition, except this one is a bitwise AND operation. But this is actually easy, because with addition you have to deal with carry and all kinds of stuff like that. With bitwise AND, each column is truly independent. It does not depend on any of the other columns. So what you need to do is to look up the table. Okay, so go look up the table, and you say, okay, we have a 1 as the first number, which is the bit I of x, and we have a 1 as bit I of y. What is the result here? A 1, okay, and here's a 0. 0 and 0 is, okay, so that would explain quite a few of these. Okay, so I'm just going to handle all the zeros first. What about this one? 1 and 0. It's also a 0. So that's the result. Are we still doing okay so far with this? And then some people will say, but that's the same result as logical AND, because 9 is non-zero, 1 is non-zero, so 9 logical AND 1 should be non-zero. So they work out to be the same. What is the big deal? What about the whole big confusion thing? Well, let's pick a different number. Okay, let's say 9 bitwise AND 2. Okay, I mean 1 and 2. I mean, what is the big deal? It's just 1 off, right? When you look at those as binary numbers, they're really quite different. So we'll deal with the second one, 9 ampersand 2. Okay, and 9 is still the same one. Okay, 0 0 0 0 1 0 0 1 in base 2, and 2 is 0 0 0 0 0 0 1 0. Is that okay so far? Okay. Now we'll go ahead and perform the actual operation. Here's the bitwise AND. And what do you think is the result?
0 0 0 0.
All zeros, right?
All.
Like that. Oh, But that's false, right? So this time, whether you use bitwise AND or logical AND makes a difference. Now this is the kind of thing that can get people into really big trouble, because when you test a program and the test cases just somewhat works out to be 9 and 1 or something like that, where the bits share positions, then the problem will not show up. On the other hand, if the two numbers do not share ones in the same column, like in the second case between 9 and 2, then the problem shows up. Because if you intend to use logical AND, then the result is supposed to be non-zero. But if you accidentally use bitwise AND instead of logical AND, then the result becomes a 0. And your program will misbehave because it will take a wrong branch. Because typically a logical AND is used in a conditional statement, in the condition of a conditional statement. So this will lead your program to the wrong path. But when you look at the program, it looks right, because a single ampersand, it still looks like logical AND, but it's not. Are we doing okay so far with this? Okay. Let's take a look at another one. Let's look at bitwise OR. Okay. So bitwise OR is not as bad, okay, because when you have 0 or 0 is 0, that's the only case. So bitwise OR let you get away with a lot of wrong stuff. If you use it incorrectly, it will let you get away with it for the most part. Okay. So if there are no questions about this one, we will move on to something that is non-existent in other languages. And this one is Bitwise Not. Okay. Now Bitwise Not is a very simple concept, and it is similar to logical not. So when you compare these two tables, you can see that one is exclamation point and the other one is the tilde symbol, which is your kind of like the shift version of the upper left corner key. Okay, the same thing as the backtick. Okay, all right. Well, the bitwise not operation is useful in many cases. Okay, in this class, we may not use it as much. So I'll give you an example. So let's say we're dealing with 9 again. Okay, so here's 9, 0, 0, 0, 0, 1, 0, 0, 1 in base 2. So if you want to look at the bitwise not or bitwise negation of 9, okay, so here's the bitwise not. It will just flip all the zeros to ones and all the ones to 0. So it becomes 1, 1, 1, 1, 0, 1, 1, 0 in base 2. That's bitwise not. It really is just looking at each individual bit position. If it was a 1, turn it into a 0. If it was a 0, turn it into a 1. Are there any questions about bitwise not, the tilde symbol? Questions about that? All right. And also in C++, we have bitwise exclusive OR. Now this one is completely missing. There are no logical operators to compare to exclusive OR in bitwise operation. So there's really not a chance of there's no chance of confusing it with a logical operator, because there's no equivalent logical operator. So for bitwise exclusive OR, you can see that 0 exclusive OR 0 is a 0, 0 exclusive OR 1 is 1, 1 exclusive OR 0 is 1, and then the last one is the only one that makes it different from a regular disjunction, which is 1 exclusive OR 1 is a 0. This one is the same thing as either or. Okay, so you only want one and only one side of the exclusive OR to be true for the whole thing to be true. Are there any questions? No questions. So we'll do a few exercises, okay, before we move on to bit shifting. So let's go ahead and deal with this. Okay. So let's try something like this. Okay, 5 or 7, and then the whole thing ampersand 2, and then we'll take the bitwise not of this whole thing, and I'll make it clear that we are dealing with 8-bit integers, just so that we don't have to write a whole bunch of leading zeros. Okay. So let's figure out what to do with this one. First thing, convert everything to base 2, because as the name implies, bitwise operation only works when you look at individual bits of an integer. It does not work when you look at the entire value all by itself. So the first thing we want to do is to convert everything into base 2. So I'm going to repeat the whole expression, except all the values will be in binary. 5 is made out of 1 and 4. Okay, so it is 0, 0, 0, 0, 0, 1, 0, 1. This means we have 1, 1, and 1, 4. Okay, 4 plus 1 is 5. 7 is 1 plus 2 plus 4. So this becomes 0, 0, 0, 0, 0, 1, 1, 1. 1, 1, 1, 2, and 1, 4. Are there any questions about the base conversion of 5 and 7? 2, well, we did it before. 0, 0, 0, 0, 0, 0, 1, 0. Okay, so now that we have everything expressed in binary, we can now carry out the innermost operation first. In other words, we're going to carry out the bitwise OR between these two binary numbers. So I chose these two numbers because they're really easy to work with, because basically if there's a 1 in a particular bit position on either side, the end result will end up with a 1 in that same bit position. So in this case, we have 5 leading zeros, and in both cases. So we know the bitwise OR of a 0 and a 0 is basically a 0. So that means if I need to rewrite this one, okay, it will start with 5 leading zeros. This one here is both numbers have a 1 at this particular bit position, which is bit 2. So end up with a 1 here. With bit 1, we have a 0 here, but we have a 1 here. I just need to have one side to have a 1 in order for the whole thing to be a 1. So this one becomes a 1. And with bit 0, this is a 1, this is a 1, so the end result is also a 1. In other words, I have now computed the bitwise OR expression, and we just have the bitwise AND operation left. Okay, that is correct. There we go. So with the bitwise AND operation, the result is a 1 if and only if both sides have a 1. So you look at all the bits here. These are 5 zeros here, and it's only matching 5 zeros here. The end result cannot be a 1, so we have 5 zeros. And then when you look at this particular bit position, this is called bit 2, and this is the same thing. This is bit 2 of the other number. They're not both 1s, so we know the result is going to be a 0. We look at bit 1. It's a 1 here. It is also a 1 here. Okay, we can end up with a 1 here. And once again, we have 1, 1 on the one side, 1, 0 on the other side. The end result is a 0. So now we have just the bitwise NOT operation left. And then for the bitwise NOT operation, we flip all the zeros to 1s and all the 1s into zeros. So now we have 1, 1, 1, 1, 1, 1, 0, 1. And that is the result of this entire expression. Are there any questions about bitwise operations? No questions about bitwise operations? Now, I do want to explain why bitwise operations are of any significance in programming, because it seems like we're just playing with zeros and ones, but why is it even useful? Does anyone want to kind of talk about that? Why bitwise operations is useful? Go ahead. Oh, you want me to talk about it? Okay. I was asking, do you guys want to volunteer and explain why bitwise operations are actually useful? Okay, so I'll go ahead and explain it. Bitwise operations are very useful for low-level access to hardware. Okay. Now, when you're just programming, working with numbers and stuff like that, doing calculations, obviously bitwise operations are not particularly useful, because most of the time you're dealing with integers or floating point numbers or real numbers and not really working with individual bits. But when you're dealing with input-output of a computer, zeros and ones become extremely useful. So what I'll do is I'm going to show you, kind of thinking, what would be a good example. I have a few, but I'm just thinking about one that you guys would relate to. So I'm digging up a particular Intel document here. This is for I/O controller input output. I/O is the abbreviation of input output in computer science. It's an abbreviation that is used a lot. ICH10, is an entire family of controller hub. So, and as you can see, this is a really long document. Okay, really, really long. I'm going to go to a particular page. So we'll go to. Okay, how do I get to a page? I'm just looking for a place where it has a. There we go. This is a good one. All right, so let's take a look at this one. This is a particular I/O register. Okay, and look at the specification here. Okay, I know this is way beyond the scope of this class, but I just want to show you what people have to deal with when they write device drivers. Okay, and by the way, are device drivers useful or important components of a computer?
Yeah.
And without device drivers, what would be the result without device drivers? What am I looking at here? A heater, right? It blows out hot air, and that's about all it can do. Okay, because I don't care how smart the program you can write. Okay, in other words, you can write the most complicated software that can predict the future. If there's no way to get information into the computer, what is your program going to use for computation? There's no input, right? Now, let's say it has all the input and it can predict the future. How does it tell you about the prediction if there are no output devices? It cannot. Right? So eventually, every single computer needs to have some kind of input and some kind of output. And the I/O registers, basically is kind of like this. So what I want to do is just to direct you to pay attention to the two columns. And I'll just go ahead and magnify so that we can read the description a little bit better here. And you can see the bit specification here. Now, this is a notation that basically says within a 64-bit word, this is going from bit 56 to bit 56 to 63. So there are how many bits here? There are 8 bits. Okay, so these 8 bits together would have the function of whatever is being described on the other side. And you can also see in the description itself, right there, it says if bit 11 of this entry of this particular I/O register is 0. Now, how do I know whether bit 11 is 0 or not? You can do a bitwise AND with an integer where only bit 11 is a 1, everything else is a 0. So after you perform that bitwise AND operation and the end result is a 0, that means that particular bit is a 0. If the end result has only bit 11 turned on, that means that particular bit was a 1 before you quote-unquote mask it. Okay? So that is why this is an example of why bitwise operations are so useful when you're dealing with low-level programming, mostly device drivers or anything that has to do with input and output in a computer. Are there any questions about this part? No questions. All right. So I'm gonna get rid of this one. And then we'll go ahead and move on and talk about bit shifting. Now, bit shifting, once again, is also a low-level feature in C and C++. The operators that we are dealing with is 2 less than symbol for left shifting and 2 greater than symbols for right shifting. So let's take a look at what do we mean? What do I mean when I said left shift? So this is an example. Let's say we're dealing with 4-bit numbers because I don't want to write a whole bunch of zeros and ones. So if we're dealing with 4-bit numbers, and this is the original value of the number, which is 1011 in base 2, if I left shift it once, that means I am taking this bit pattern here and basically move the whole thing to the left-hand side by 1 position. Now you can shift by any positions if you want. Okay, you can shift by 5 bits if you want. But whatever amount of bit position you're shifting, you're basically just moving the entire pattern that many bits to the left-hand side or the right-hand side if you're dealing with a right shift operation. But the question is, what about those bits that get shifted out of the number? Well, they're lost. Okay, that's the only thing you have to say is they're lost. Okay, so in this particular case, because I'm shifting by only 1 position, the leftmost 1 bit, which is this one here, is basically lost. Then what become the new bits, right? Because if you're dealing with a bit shift operation, obviously some new stuff is coming in from the right-hand side in this case, because the whole pattern is going to the left-hand side. So what is coming in from the right-hand side? In this case, it is just a 0 coming in. Are we still doing okay so far with the concept of bit shifting? Any questions about this part? Yep.
You said a 0, only a 0 comes in?
Yes. When you're bit shifting, the new bits that are introduced into the number, they're all guaranteed to be zeros. Okay, let's do an example. Let's go ahead and work out an example here. So I'll just give you the base 10 number first, and then we'll work out, how it will all work. How we'll work out the result. So let's say we're dealing with let's pick 11. Okay, so we'll pick 11 here, and then we'll shift it to the left-hand side by 3. Okay, and this time we're dealing with base 8-bit numbers. Okay. I cannot do any bit shifting until I know the representation of the number in binary. Okay. Well, I can actually do it, but I'm not going to explain that part until we're done with this one. So 11 is 1 plus 2 plus 8. Okay. 1 plus 2 plus 8. So we have to choose the right bit positions. We have 1 1, 0 2s, 1. No, I take it back. 1 2, and 0 4s, and 1 8. So 1 0 1 1 in base 2 is 11. But since we're dealing with an 8-bit number, I'm going to give it all the padding zeros. So that now we have exactly a number that has 8 binary digits. And we want to shift everything to the left-hand side by 3 positions. So what we'll end up doing is these 3 bits, these 3 most significant bits, will be shifted out of the number and will be lost forever. Okay? And then the other 5 bits, these 5, will become the most significant 5 bits of the result of the bit shifting. And then we'll introduce 3 additional zeros on the right-hand side. So the end result of this is 0 1 0 1 1. Okay, so you can see basically these 5 bits, instead of being the least significant 5 bits, will now become the most significant 5 bits. But we'll also introduce 3 additional zeros on the right-hand side, just to make up for the number of bits here. And that's the end result. What is the value of the end result? That's the next question. Okay, now we can see the binary representation, but what value is it really representing? Well, there are 2 ways to work this out. We can look at all the individual bit positions. This is representing the 64s, 16s, and 8s. So we have 64 plus 16 plus 8, which is 88. Wow, 88 and 11 aren't they kind of connected in some way? Well, 88 is 8 times 11. Does that have anything to do with 8 is 2 to the power of 3? What do you think? Absolutely. Okay? Every time you left shift by one position, you're multiplying by 2. Okay, wait. Okay, let's think about this one more time. Every time we left shift a binary number by 1 bit position, it's the same thing as multiplying the value by 2. Does that make any sense? Well, okay, let's think about base 10 numbers. Okay, in a base 10 number, if I say, okay, pad 1 0 on the right hand side, what does that do to the value it is representing? It becomes 10 times the original value. So, but that's because in base 10 numbers, the base is 10. In base 2 number, the base is 2. So every time you introduce a 0 on the right hand side, you're doubling the value that is being represented. So what if I double the same thing 3 times? It's times 8. Because you double once, it is times 2. You double twice, it is 2 times 2, which is times 4. You double it 3 times, it becomes 2 times 2 times 2, which is 8 times the original value. In other words, if you know that you are multiplying by a power of 2, left shifting can do it for you. But only when your multiplier is a power of 2. Are there any questions about left shifting? Yep.
So if you left shifted by 4, then
That'll be the same thing as multiplying by 16. But that gets tricky with this one, because with this one, we'll end up with a, depending on whether the integer is signed or not, if you left shift it one more time, it becomes a negative value. In other words, remember the wheel of numbers? If you left shift it one more time, we are running out of values. Yep. All right. Let's take a look at another example. Let's take a look at let's see, 100 right shift by 3 times. Okay, so that's a good one, because if I do it only twice, it would still be a whole number. Because most of you are now thinking, if left shifting is the same thing as multiplying by 2, okay, every 1 bit you left shift is multiplied by 2, then every 1 bit that you right shift by, is going to be a division by 2, right? Kind of works out that way. No? Okay, if I give you a base 10 number and I say, move all the digits to the right hand side by 1 position, it's basically the same thing as dividing the number by 10. So when you do the same thing with a binary number, it is the same thing as dividing the number by 2. Okay? But in this case, something is not going to work right, because 100 is not divisible by 8. So let's go ahead and figure out what's going to happen here. And the first thing we want to do is to figure out what is the base 2 representation of 100. So 100 is what? 64 plus a 32 plus a 4. Is that working out? My arithmetic is awful, so I just need you guys to kind of double check for me. Yep, it's good? Okay. So we want to represent it as a binary number. So we have to figure out, we have 0 1s, 0 2s, 1 4, 0 8, 0 16, 132, 164, 0 168 as a base, as an 8-bit number. Is that working out okay so far? Did you guys kind of work out, huh?
You meant 128, right?
0 128. There are no
168.
Oh, sorry, 128. Sorry. So that's how I come up with a binary number, and we want to right shift this number by 3-bit positions. So right shifting is kind of the opposite of left shifting. We take we look at the 3 least significant bits, which are these 3 guys, and we say, okay, we'll toss them away because they will be shifted out of the number. And so what are we going to do with the other 5 bits? These 5 will become the least significant bit of the new number. that's easy. 0, 1, 1, 0, 0 become the least significant digits. But we need to specify what rolls into this number. And in this case, we just roll in 3 zeros. Kind of the same way as left shifting, we introduce zeros into here. So that's the result of the right shifting. So let's figure out what this binary number is representing in terms of quantity. And we have 0 1s, 0 2s, 1 4, and 1 8. 4 plus 8 is 11. 12. I'm sorry. This makes me a really perfect liar because I can give you the wrong answer without intending to give you the wrong answer. In fact, I was intending to give you the right answer, but it just came out in the wrong value. Okay, so this is actually 12. Okay. 100 divided by 8 is 12. Well, it kind of works out because it is only keeping the quotient of the division. The remainder is basically rolled off. I mean, we lost that one. Do we have any questions about bit shifting? No questions about bit shifting? How many people are used to the RGB representation of colors? If you program in HTML, you probably know a little bit about representing RGB in a hexadecimal number, sort of. Okay, so it's not uncommon that in HTML code, if you want to specify a particular color, you can specify a huge number. Okay, most people use a hexadecimal number for that purpose, but that's not the only way to do it. So let's take a look at how to specify RGB as a number, making use of the stuff that we have talked about today, because I think that might be related to some of the stuff that you might have to do occasionally, okay, just to work with HTML coding. Okay, so we'll want to take a look at let's see, pink. Okay, so what are the RGB value for pink, the color? RGB, okay, for red, green, and blue. Now I can give you an idea. Each color can go from 0 to 255 in most RGB representation. You basically have 8 bits for each color. So if you have R, G, and B all being 255, what do you get? What color do you get? A white pixel, okay? Because it has equal amount of R, G, and B. And what do you think will happen? What do you need in order to make it pink? Which is not saturated red, it's just, with a lot of white components in it. What do you have to reduce? The green and the blue, right? So you will go ahead and reduce the green and the blue. Let's say we reduce both of these by 55, so that this is 200, and this is also 200. That will make a certain pink color. Which shade of pink, I'm not quite sure, but it's going to be appearing as a pink color. So now we want to say, okay, now that we know what the RGB components are, how do we come up with the 32-bit number that you have to specify in HTML to specify the pink color? Now when you specify RGB in HTML, you can look it up. So you can just look up HTML RGB code, and you can kind of tell the way it works. These are all saturated ones, and here we have some pink colors. Is that kind of pink? Yeah, it's more purple, So we want a red, we want full red, and then we just want the blue and green to be turned off. This is more pinkish. Is that okay? Does it look pinkish to you? Okay. So you can see that this one has, this is in hexadecimal number, okay? In other words, each digit is a base 16 number. Now, when you deal with, I'm not going to deal with your base 16 number, But basically, this is the code that you have to enter when you specify the color of pink if you want to use hexadecimal numbers. But you can also do it in base 10. Okay, so what we'll do is we'll look at this number. Let's spell out how a RGB value is represented as a 32-bit number. So we'll deal with the 32-bit number here. As a 32-bit number, the most significant 8 bits are not used. Okay, sometimes it's used for alpha, but in this case we'll assume it's not used. You always put a 0 here. The next 8-bit numbers, the next 8 bits will specify the R or the red component. And then we have the G, the green, and the blue component. Okay, so as a 32-bit number, it's broken up into groups of 8. The most significant 8 bits are not used. Keep those zeros. The next 8 bits will specify the red component from 0 to 255 because there are 8 bits there. And then the next one is green, and the last one are the blues. Okay. So if you want to specify the pink color the way we want to specify here, one way to do it, I'm just going to give you the solution here, is to say, okay, whatever the red component is, shift it by 16-bit positions. And just to make sure that we understand the order of operation, I'm going to put parentheses. And then the blue component is going to, G green component is going to be bit shifted by 8 times. And then the blue component is just the blue component because it is not going to be shifted in any way. So if you know ahead of time, as each individual being from 0 to 255, this is how you mix the RG and B together into a 32-bit integer that you can specify at wherever a color is expected. Is that working out okay, or more or less? Yep.
Why did you move each color by 16.8? How did you choose that?
Because the R component, okay, R by itself is a 8-bit number from 0 to 255. And same thing with G and B. But I don't want R to be all the way over here, because if you do not shift it, it is automatically just the least significant 8 bits. So by shifting it 16 times, just this component is going to be R, followed by 16 zeros. And then this one is going to be G, followed by 8 zeros. But the bitwise OR is going to work out just fine because the component where G is supposed to go is going to be all zeros in this particular expression. So that's why this is going to work out, because by shifting, I'm introducing just zeros with the other bit positions, and so the bitwise OR operation is going to work out just fine. Are there any questions about this little expression here, which is a quick way to mix R, G, and B component into a particular color specification in HTML? No questions? Does anyone program in JavaScript so they can play with stuff that's interactive on the browser? If you do that, this comes in handy because it allows you to write a program where you can change the color of something on the fly, with JavaScript, so when people look at your screen, you can set up a timer so the background color can change, like gradually or something like that, because it allows you to mix the colors, on the fly whenever you need to. Yep.
So do we lose all the red if it shifts 16 to the left?
No, because this is a 32-bit number.
Wouldn't the R be in the second 16th or the second 8th?
Okay, so let's take a look at, let's plug in some values, okay? So let's plug in some values here. So let's say R is 255, which is 1111 in base 2, okay? G is 200, and 200 is 128 plus 64 plus, that would make 192 plus 8, so that would be 1, 1, 0, 0, 1, 0, 0, 0 in base 2. Okay, did you guys double check my math? my math is usually pretty bad. 192 plus 8, so I think that's right. Okay, and then B is the same. Okay, so let's pick a different one for B. So let's pick 192 for blue. Okay, just so that the bit pattern is not exactly the same. So that's easy because that's just 128 plus 64, which is 11000000. Okay. So once you plug in R into here, G into here, and B into here, what bit pattern am I going to end up with? 00000000, and the red component is shifted 16 times. Okay, so let me just kind of work out the whole thing. 1111, 1111, followed by 16 zeros. Right? This is coming from this expression. Are we doing okay so far with that one? Is that okay? And the next one, okay, I'm just going to use a bitwise OR here to mean it is bitwise OR. The next one is green. Green is this particular bit pattern, and it is left shifted 8 times. So that means we will have 11001000 followed by 8 zeros here. Are we doing okay so far? This is the base 2 representation of G left shifted 8 times, and G being 200 in base 10. And then we have one last one, which is the blue component. The blue component is not left shifted in any way, so we are just going to keep this bit pattern here in the bitwise OR operation. So when you look at this entire bitwise OR operation, then you can see that it's going to be 1111, 1111, 1100, 1000, 11000000, and if you prefer to look at this as a 32-bit number, you can always pad as many zeros as you want on the left-hand side to make up 32 bits.
I think my misunderstanding was I thought they were all one 32-bit color instead of each individually.
Oh, okay. Yeah, each one is only an 8-bit number, because in most RGB representation, they only give you 256 possible levels, because 0 is one of them, and that's why the maximum value is 255 and not 256. And this is how a GIF also works out. In GIF, it has a table, color table, and then each color entry in the color table is also in RGB format like this. All right. Well, so this is one, real actual application of bit shifting and bitwise OR. So, any questions? Yep.
If we're doing this, is there a shortcut? Something we can use to do this a little bit faster?
To do it faster?
Yeah.
Oh, if you just plug in this particular expression, it will do it for you. That's why I give you that particular expression.
So when you write HTML code, you actually have to input.
When you write HTML code, you have to input the actual number. And for those of you who write HTML, you use a pound sign to indicate this is a base 16 number. Yeah, I think it's a pound sign to mean the base 16. But instead of using a base 16 number with a pound, you can always plug in a decimal number using this calculation. All right. Well, since we're here already, we might as well kind of talk about base 16 numbers. Did I talk about base 16 number in this class briefly? Okay. Now, between base 2 and base 16, the conversion is easy. Because what you do is you group bits into groups of 4, and then you look up a table to look up, okay, these 4 bits collectively is this one single digit in the base 16 number. Okay, so I'm going to do it here. We'll deal with these 4 bits first. Okay, 1111 is F as a hexadecimal number, base 16. These 4 ones will be an F2. 1100 is a C in hexadecimal, and this is an 8 in hexadecimal. F again, and a 0. So as a base 16 number, this is the same thing as a FF C8 F0. And oops, I said one thing and I wrote down another thing. This is a C, sorry. 1100 is a C. So if you plug in, pound FFC8C0, then you should get something that is kind of like pinkish in color. And so you can see that the conversion from base 2 to base 16 is really kind of easy. Okay, once you can remember a 16 entry table, it's all like you can do it almost instantaneously. Okay, any other questions? How many people know a little bit about networking because you have to set up like a Wi-Fi network or something like that at home or something like that? Okay. Do you guys remember that in many places you see what we call a bit mask or a net mask, which is usually 255.255.0. Yes? Kind of? No? Okay. Do you know what those numbers mean? Sort of? A little bit? No, not the MAC address. Okay. So I'm just going to talk about it a little bit here because those are also bitwise operations. Okay, so it is really helpful to understand what those numbers are really for. Okay, so most of you, when you set up a Wi-Fi network, you will end up with each machine or each interface ends up with an address like 192.168.1.56, right? That's a fairly typical IP address that you get from a home router. Okay, but the bit mask is usually 255.255.255.0. So this is what we call an IP address, and this is what we call a net mask. Okay. Now 255 is kind of a special value because now we start to understand why 255 is such a kind of important value because it is all ones in binary. So what this really means is when you look at an IP address, okay, so the bit mask or the net mask is basically 1111.1111, and repeat that 3 times, and then we have just zeros here. Okay, so basically it is looking at each IP address, which is a 32-bit number, and it will say this part is the name or the address of the network, of the entire network, and then the zeros would be corresponding to each particular interface. That's how this particular network is set up. The most significant part, the part that is corresponding to all the ones, is kind of like an area code because that's the prefix of all the IP addresses of what we call the subnet. So it's kind of like an area code. And then the only part that specifies, that can differentiate one interface from another interface of the same subnet is this part here. So if you look at this number here and convert each part into a binary number, this is also a 32-bit number because each component between the dots is an 8-bit number. So bitwise operation is also useful in networking. Okay. It's just that we don't really learn a lot about networking in programming classes, but if you want to play with those IP addresses and whatnot, they're all basically binary numbers in the end. When was the last time you saw a hexadecimal number, in a networking setting? How many people kind of mess around with your MAC addresses? No, not really. Okay. Do you set up your own router at home? Okay, so it depends on your provider. Some providers use the MAC address to identify who you are. Okay, so every time you sign up with, let's say, Shore West, okay, they will ask you, okay, give us your MAC address so they can configure their router so that when you try to connect, they know you are a paid customer and they will assign you a particular IP address. And what does a MAC address look like?
Letters and numbers with colons.
And those are all hexadecimal numbers, and there are 6 components. Each one has 2 digits. And so together it is a 48-bit number. Basically, it's a 48-bit sequence, but it is written as 6 chunks, and each chunk has 2 hexadecimal numbers. Right. So we are done with logical versus bitwise operator, and base conversion and bitwise operator as an exercise is now open. Now this is, I'm just going to click on it so that we can
We're allowed
take
as
a look.
many times as we want. We're allowed as many times as we want.
Okay, so here's the deal. The deal is the quiz will close basically 1 week from today. Okay, so starting at 9 a.m. So it will close at 9 a.m., which is right before class. I think with this one, you can turn in as many times as you want, and it will grade it for each one. So you can try again and again and again. So you have an unlimited number of trials before the due date.
Okay.
And I think it counts the highest score too.
Okay.
So it definitely have plenty of time to play with it. Are there any questions about bitwise operation? Okay, if there are no questions about bitwise operation, we're going to move on. So don't forget, this is your current homework assignment, is to understand and work on bitwise operation. But as far as the lecture is concerned, we are moving on. Okay, we're moving on to typecasting, coercion, and promotion. Okay. Now the rationale of all of this is because we have different types of integers of different types in C and C++. We have 8-bit integers, 16-bit integers, 32-bit, and 64-bit. Okay. So the question now is, if I try to use different types of integers and kind of mix them up, can the C and C++ compiler deal with it? That's the question. Okay, so I have one example here. So with this one single example, I use this type to define big int. Okay, so big int is a signed 32-bit integer. We have little int as an 8-bit integer, and I put a 0 into little int, and then I perform some calculation with little int and store that into big int, and then I do something with big int and store that back into little int. So even to us, it doesn't look like there should be really a lot of problems. Well, I wouldn't call those problems, but there are some issues that need to be dealt with. Okay. So the question now is, what happens when we have on one side, well, this looks like this is going to be an 8-bit number, and then on the other side we have what is a 32-bit number. So the question is, how do we deal with something like that? Okay, that's the question. So we have coercion here. Okay, so these are all about coercion. So coercion in C and C++. Let me roll back to typesetting first. Typecasting first. Typecasting refers to the operation that converts a value of one type to a value of a different type. So you can basically force the representation of a number to 8, 16, 32, or 64-bit wide. In the current context, this means a conversion from one integer type to an integer type of a different width. And coercion is basically automated typecasting. The compiler is doing it for you. This one doesn't look like there should be a coercion, but there's one. Okay, if you read the text, you'll find out the rest. There's a coercion here, because when you just say a constant like 0, okay, it already has a type associated with it. When you just say 0, the type is int, int all by itself. So that depends on the platform that you're using, that you have the tools installed. If you're dealing with a 32-bit platform, int all by itself is basically the same thing as int32_t, which means integers have 32 bits. So that means when you just specify an integer constant all by itself, like 0 here, this is not just 0. This is 0 in 32-bit representation, which is extremely boring, right? Because 0 as a 32-bit number is just basically 0 repeated all 32 times. But the problem is the other side, the left-hand side of the assignment, is little int. Little int only has 8 bits because of the way I specify the type. when you specify the type int8_t, it means I want an integer, but this is going to be a small integer. It only uses up 8 bits. So now we have a problem because I'm trying to store 32 bits into 8 bits. Yep.
Did you say that 32 bits is like standard for any type of like zero?
It depends on your platform. In other words, if you install GCC on a 64-bit installation of Linux, that particular GCC will consider 64-bit as the quote-unquote default size of an integer. With a 32-bit platform, it is, the default size is 32-bit. So it depends on, the target platform of GCC. If GCC is targeting a 32-bit system, an integer all by itself, int, is 32-bit wide. And without specifying anything else, 0 or 1 or any other integer constant that is spelled out by default is 32, is the default width of int itself. Anytime you have 32-bit on one side and 8-bit on the other side, or the width do not match up, then you have to decide, okay, what are we going to do? Because we're trying to store something that has 32 individual bits into a variable that only has 8 bits here. Well, as it turns out, the compiler will try to figure out most of this stuff for you. So in this case, it would just drop the most significant 24 bits and store the least significant 8 bits. That's what the compiler is going to do. But that's all done without having you to know anything. You don't have to specify any type of typecasting, and that's why it's called coercion, because it is done automatically by the compiler. Now, on the second line, where do you think the coercion is happening? We have 2 operators, and every time you have an operator, there's a chance that there's a coercion. So the question now is the coercion, which is an automatic type conversion, is it happening for the assignment operation, or is it happening when you're performing addition? What do you think? Coercion needs to happen every time you have a different width, okay, with an operator. Okay, the answer is the plus. Okay, the plus operator is the one that triggers a coercion in this case, not the assignment operation. Let me explain. Okay. Now, if you just look at this entire statement, okay, what needs to happen first? The assignment or the addition? The addition needs to happen first. Okay. So when you look at the addition, and you look at the 2 sides of the plus operator, what is the width of this guy here? How many bits? 8 bit. And what about this side? It does not specify the actual width because it is a literal constant. But remember what I said a little bit earlier? If you have it's 32 with a 32-bit platform, right? So with that assumption, we have a difference here, because on one side of the addition, you're dealing with an 8-bit number. On the other side of the addition, you're dealing with a 32-bit number. So what happens here is the coercion will also happen, which means you don't have to do a single thing, the compiler is going to do it. And in the case of addition, what the compiler is going to do is to promote little int to 32-bit first. And then we have 2 32-bit numbers, so the addition can happen. But what that also means is by the time we have the sum of these 2 numbers, it is already a 32-bit number. And as a result, when we perform the actual assignment operation, there's no coercion needed for the assignment operation because the entire right-hand side of the assignment operator is already 32-bit wide by the time the addition is done. So the coercion only happens once when we're dealing with the addition, not when we're assigning. So it's a little bit tricky, okay? It is a little bit tricky because you have to figure out when do we have a different size on both sides. Okay? Same thing here. Now, with this line here, when do you think the coercion happens? There's one, okay? It happens only once, but you have to figure out when it is happening. The assignment, exactly. Because in this case, the addition still has to happen first. But the question is it going to trigger a typecast, automated typecast operation? So you look at this addition here, you look at the left-hand side. The int is a 32-bit number. 1 as a literal constant is automatically the default size of an integer, which is also 32-bit. So as far as this addition is concerned, you are adding a 32-bit number to a 32-bit number. Well, we don't need any coercion. They're of exactly the same width. The sum itself is going to be 32-bit wide because they always have the same width as the individual parts. But where we want to store it is only 8-bit wide. So once again, we end up with a situation like the first one, which is we want to store a 32-bit number into an 8-bit integer, and the result is it has to do a typecasting. So in this case, just like the first case, we will lose the most significant 24 bits and only store the least significant 8 bits into the variable. But that means there's a potential problem here. Okay? Potential problem, which is not happening in this specific case because of the numbers that we chose to use. So what if the big int actually has a number that cannot be represented as an 8-bit number? You will lose the most significant part of it. Okay, so let's go ahead and take a look at a few examples related to typecasting issues. So let's say big int has a value of, I don't know, let's pick 487. Okay, that's base 10. And then we say little int is store whatever is in big int into little int. Okay, and we keep the same definition, the same declaration of big int and little int in this example. So the question is, if I examine little int, what is it going to store? What is the actual value stored in little int when I look at it all by itself? Well, first thing first, little int is an 8-bit number. What are the possible values that I can store as an 8-bit signed integer? Remember the number wheel thing, okay, or the range of values that we can store? Okay, I'm going to rewrite that equation here. You don't have to write it down, it's in my notes already. The most negative value is negative 2 to the power, negative 2 to the power of w minus 1. That is the most negative value you can represent, where w is the number of bits of the integer. So in this case, because it's an 8-bit number, it will be negative 128 on the negative side. On the positive side, it is 2 to the power of w minus 1, and then the whole thing minus 1, which in this case is 127. The value of 487 obviously is out of this range. So that means when we perform this particular assignment, something is going to be lost. So the question is, after this assignment, if I just look at little int, what is the value that is stored in little int? That is the question. What do you think? Okay, there's one thing you can do first. Okay, so what you do is you say, okay, so 487, you can always look at the representation of 487. So you can look at the representation of 487, and I will be very lazy here, because I'm just going to say it's 256 plus some bits, right? So if there's a 1 for the 256-bit position, and then it has some other bits here. Is that okay? I'm just being lazy here and use a question mark for the placeholder. So when you look at little int after the assignment is only going to be the question marks. That 1 is lost because it is not a part of the least significant 8 bits. So whatever the question marks are in 487 is going to be the value of little int. Okay? But that's a problem because we are losing something, and in the assignment operation, the value in the variable little int is not really the same value in big int. So the next question, the really obvious question is, should this be considered an error? and I think it should be. But C will just do this silently, lose the most significant bits, and not tell you a single thing when you're losing something that is actually important. If you're only losing all zeros, it's not a problem, right? It's not actually going to change the value represented by the number. But if you're losing something like this, a 1, that is actually significant, you will be changing the value being represented in little int. In many programming languages like Visual Basic or some other programming languages where you can specifically say, I want a particular type, and it doesn't fit, it will give you a runtime error. Okay, it will basically do a runtime error, pop up a screen and say, hey, we have a problem here. We want to store a value that cannot be stored into the destination, and it would just stop and scream and say, okay, we cannot move on from here on. But C doesn't do that. It just silently goes through this whole process, and it just pretends that nothing happens. So what does it mean to you as the developer, the person who's going to write programs? Say again? Yep, as a developer, as a programmer, you are the one who have to make sure that you're not going to lose something that is important when you have this type of situation where you have a larger integer to begin with and you're going to store it into a smaller integer. Okay, because the compiler does not complain, and it will silently fail when it runs. Are there any questions up to this point? Yep, go ahead.
So when you lose that significant digit, the 1, what does little int replace that with to make up the 8-bit?
Oh, it will keep the least significant 8 bits. In other words, whatever these 8 bits are, it will keep those. Yeah. So let's see if we can do this part here. So 487 is 256 plus. Is there 128 in here? Yeah, there's just barely 128, right? No, it's not just barely. So plus 128 plus. Oh, my math sucks. That's why we have a spreadsheet. And we still had some here. Okay, let's start a new one. So the number is 487, right? So 256. And this is going to be this number divided by 2. And we'll say so if C1 is greater than or equal to B1, this is a 1, this is a 0. Keep flipping the this number minus this number times this number. There we go. So now we have the binary representation, which is 1 1 1 1 0 0 1 1 1. Okay. Okay. Switching back to here. Okay. So big int in terms of a binary representation is 1 1 1 1 0 0 1 1 1 in base 2. So that means in little int we are going to keep 1 1 1 0 0 1 1 1 in base 2. Is that okay so far? Now, when you look at 1 1 1 0 0 1 1 1 in little int, I'm just going to ask you, do you think it's a positive number or a negative number?
Negative.
It's a negative number. So not only are you losing something in the original value, you're also turning a non-negative number, which is 487, into a negative number, which is not good. And I can almost tell you what negative number is going to be represented to. There's an 8 and there's a 16, so it's a 24. So this is actually representing negative 25. So you store 487 into a smaller integer, and you end up with a value of negative 25. Just imagine what's going to happen when your program try to access little int and thinking, hey, it has the same thing as big int earlier. Nope, not even close. But the compiler won't complain when you're translating from C code into machine code, and it won't even do a single thing at runtime. It won't complain at runtime and say that, hey, this is a problem. Nope. It will just do it without warning you whatsoever. Okay. Are there any questions about this little exercise here? We'll go ahead and take a break. I know I'm ending the lecture a little bit late, so I will give you guys 10 minutes to take a break. And then when we come back, I'm going to go into GCC and GDB. Okay, so we'll go ahead and try to see how can we look at these operations, but from the perspective of actually writing some C++ code and use GDB to help us understand, okay, how do we test this stuff, okay? Tech keeps talking about all of this stuff here. How do I verify this is actually what is happening in an actual program? So when we come back, we'll do that, okay? I'll stop the recorder now.